not great notation, but I'll just say delta S2 in delta T1. I refer to delta T1 because that's a delta S that we're going to get in the delta T1, the time it takes to get the first ball to the end of its ramp. And that delta T1 is 1/7 of a cycle. So to get the delta S2, we're going to multiply the average velocity of the second ball in this T2 interval. So I'll put the T1 interval. Let me fix that. Okay, so the V bar to delta T1 stands for the average velocity attained by the second ball between here and here, where the time interval is delta T1, the time it took the first ball to get to the end of the ramp. We multiply that by the delta T1, which is how long it's been going, and we get the delta S, okay? Now, what's V2 in delta T1? Well, the final velocity in delta T1 is this. So we could even say that this is VF in delta T1, okay? And it follows then, since the initial velocity is 0, that the displacement during delta T1, the displacement of this ball, well, it's going to be governed by the average velocity, which is going to be, since the initial velocity is 0, half of the final velocity, half of the 5.1 centimeters d per cycle. So, and I should add one more thing here. I'm going to call this VF2 in delta T1, okay? Final velocity of the second ball. So that when I write this, V bar 2 in delta T1 is approximately 2.6 centimeters d per cycle. And that's obtained just by taking half of this and rounding to two significant figures. Okay, so the second velocity here is 2.6 centimeters d per cycle. We multiply that by our delta T1, which is 1/7 of a cycle. And we get approximately, what, 3.37, I'm sorry. .37 centimeters d. Now, where is that? Well, the ramp is 2 centimeters d long. 0.37 centimeters d is all the way back here. We don't really get very far. Now, when I drew the picture, I mean, I knew it wasn't going to go this far, and it was going to be fairly short, but I didn't know exactly where to put it, so I just drew a picture big enough to draw these arrows on. So my picture was particularly accurate, but I didn't know what the result was going to be. I had to work it out. So the result's going to be way back about here. This ball is not going to go very far in the time it takes this ball to get to the end. Okay, now let's just quickly summarize. We took our average velocity information for the two ramps and the length of the ramp, and we calculated the time for the first ball to travel to the end, just dividing the delta S by the V bar. We got 1/7 of a cycle. And we did the same thing here for the second ball as part of another calculation, but let's just observe that we just divided the 2 centimeters d by the 6 centimeters d per cycle, and we got 1/3 of a cycle, which is more than twice as long as 1/7 of a cycle. The final velocity of the second ball on the ramp, since the initial velocity was 0, you can work that through the definition of average, well, the straight line property of the real line, the expression for the average velocity, and determine that the final velocity is 12 centimeters d per cycle. And this is valid. This is one of the cases where it is valid to double the average velocity to get the final velocity, because in this case the initial velocity is stated to be 0. So now we know the final velocity on this ramp. The ball started from 0, So the acceleration being the change in velocity divided by the change in clock time, change in velocity is just going to be equal to the final velocity since the initial velocity was 0. So the change in velocity is going to be this. The time interval is going to be 1/3 of a cycle. And when we divide that, we get 36 centimeters d per cycle squared. And that's the acceleration of the second ball on its ramp. Now, why do we calculate the acceleration of the second ball? So we could answer questions about position and velocity of the second ball in the time it takes the first ball, the 1/7 of a cycle for the first ball, to get from the start to the end of its ramp. So if you start these two balls at the same time, where is this ball when this one ends, when this one hits the end, and how fast is this ball moving? And the rest of the calculation is fairly straightforward. Velocity of the second ball after 1/7 of a cycle, well, you multiply the 1/7 of a cycle by the acceleration of the second ball. This is why we needed the acceleration, and we get that final velocity, or we get that average, we get that final velocity. So this is the final velocity of the second ball after time delta t, and it follows that the average velocity in time delta t1 being, again, the time it takes the first ball to get to the end of its ramp, is going to be half of the final velocity, again, because the initial velocity is 0, that's justified. Then we use that and multiply it by the delta t1, the time that we have to go down the ramp, the time it took the first ball to get down the ramp, and we get how far the second ball traveled on its ramp while the first ball was traveling all the way down, and we get not very far, 0.37 centimeters d, when delta s is 2 centimeters d. Okay, so that's about a little less than 2/10 of the total distance, about 1/5 of the total distance down this ramp. Really short synopsis. What have we done? We found delta t1 on the first interval. We have plenty of information to do that. We found the acceleration on the second ramp, not first interval, first ramp. Find A on the second ramp. So we find delta t on the first ramp. Plenty of information there. Find acceleration on the second ramp. All the information we need is given to us. Then we find delta v, that's a comma, then vf, and then v bar on the second ramp for the interval delta t1, the delta t1 being the time it took to go down the first ramp. And then, since we've found v bar on the second ramp for that delta t1 interval, we find delta s on the second ramp for the same delta t1 interval. Now, I'll comment. I would regard this as maybe the most challenging problem on the practice test. There's another that's fairly challenging also. I'm going to tell you, you can't solve this kind of problem by imitating another problem just like it. Many problems you can, but we've worked hard to learn how to reason things out and put things together. Now still, this is very challenging even though we've done all that work, but the only way you can get to the point where you can solve a problem of this nature is by understanding very deeply what it is you're doing, and also by solving lots of problems so you get better at solving problems, better at setting them up, better at seeing what's necessary, and you simply have more experience to work within in order to solve the problem. Didn't quite have the right words there at the end, but hopefully you understand what I mean.